you make phage that had fused to their envelope protein every combination of 12 amino acids. That's what's called making a phage library, right? That's a library of what you're interested in. That's multiple phages having different peptides on them. You can, is often done is you take that phage library of, so now this would be a case you would have a known peptide, right? A peptide that you say is the most important part, say, for a signal protein. You have a signal protein, there's a 15 amino acid long section of that signal protein. That's the most important section for binding. You take that and you put that, say, 15 amino acids on the end of fuse it to a envelope protein on the phage, and then you inject that into a mouse. Right? You let it circulate through the mouse, you then euthanize the mouse, and you dissect its organs. And you look to see where those bacteriophage bound. So in that way, you can see what types of cells are binding to what types of bacteria, what types of cells are binding to what types of peptides. So then, once you can get the phage, and then you can see what those peptide sequences are that were binding to the cells. So maybe in this case, you have, again, you make 12 random amino acids. Okay? 12 random amino acids on the end of the bacteriophage, and then you go in, you want to see what are the peptide sequences which are binding to the heart cells. So then you would take the heart, dissect the heart, find what bacteriophage had bound to the heart, then sequence those peptides, and you would see these peptide sequences are interacting with the receptors on the outside of heart cells.
And why do you know that?
Well, receptors, right, but what this does is say this is one of the first steps in drug discovery. So when you have, very often the case, the signal perception by a receptor on the outside of the cell is the first step to disease. So say you had a type of cancer which was known to be, say, this protein, or you had a receptor that was never sensing or always sensing being bound to a signal protein or something. So if you could find out what what's the protein sequence that binds to that, maybe the tightest, you could then go back and design a drug that resembled that peptide, so that then it would interact with that receptor and then maybe shut it down. Right? So this is something that's typically a step of drug discovery, where you're trying to find out what's a peptide that interacts with this protein. And that protein that you're looking for interaction with is typically something that's involved in disease. So if you could turn it off or you could turn it on, you might stop disease.
I'm just confused on whether the things that you're injecting, is that actually the viruses?
Yes.
Or is it, so what happens, why is E. coli in here? I'm confused on it.
Right, so these bacteriophage normally infect bacteria, right? They'll infect bacteria and kill it, right? This is not going to kill the mouse. If you were injected with bacteriophage, it wouldn't do anything to you. But they're going to float around in your system and not cause any kind of infection. So the bacteriophage are only put into the mouse because they can selectively bind to certain things because they have these peptides on the end of there. You're looking for binding interactions. There's no infection stage.
So you just use the E. coli to make more?
Exactly. Okay.
How do you determine which phage bound to the cell?
You'd have to sequence the peptide. So you'd have phage that bound to those cells, then you'd have to take those phage off. You could then purify phage off of the cells, then peptide sequence.
But how do you know that originally it did bind to the cell?
Because if it interacts well enough, it'll be there. So you're only looking for strong interactions. So if it's only an interaction that's, say, transient, that's what you're not interested in. You're only interested in very strong interactions. expression. So this will bind and it will stay. So when you dissect the cells and purify the virus off of it, and that will have been there.
We don't know that if the virus will bind to the cell.
You don't. That's why you do millions every combination. You're just looking for 2 or 3 out of every combination you can think of. Right? It's a search. You don't know anything's going to happen.
So then we just take every cell and sequence it, every cell in mouse.
You would take right. You can separate viral particles from normal cells. So you take the normal cells that have normal cells, virus particles. Separate the virus particles out, peptide sequence them, and see exactly what the peptides were that interact with the cells.
No, you just take the tissue and you shape it of the cells, everything that might be bind.
More likely, you take the heart and like put it in a blender or something.
Okay.
Any more questions? Okay, so from that we go to as different a topic as probably possible. So just measuring protein concentration. You can turn that off.